This lecture will cover the instruments that we'll be using during this workshop, so we'll go a little bit more into the background of their theory and their uses. So here's an outline for the presentation. First, I will give differences between trace detection and bulk detection and their advantages and disadvantages. Then we'll move into the instrument detection technologies, and these include ion mobility spectrometry and gas chromatography differential mobility spectrometry. So during this workshop, we'll have use of three different instruments. The first two are bimorpho detection, and these are the Itomizer 3 Enhanced and the mobile trace, which is actually a handheld IMS that you can take out into the field. For the gas chromatography DMS, we'll be using Thermo Scientific's Aegis Defender. And I will describe a little bit about each instrument so you'll have an idea prior to getting into the lab and working with them. Lastly, I'll talk about the operating conditions optimizations that we can do to these instruments in order to enable the detection of the volatile chemical signatures that you just saw the canine hit on for marijuana. So normally, these instruments do not come with these compounds configured, so they just come with the parent drug and explosives such as RDX or THC programmed into the instrument. So through research that we have done at the Almirall lab, we've determined how to change the instrumental conditions in order to preferentially detect these compounds. So the first layer of security in an airport scenario is the metal detector. Almost all of us have to go through it, including these penguins. Then we also have X-ray systems, and here on the top right we see the VAXA system, which we'll later on see a video about. And it's scanning these porta potties at a large venue such as the Super Bowl. Below that, we actually see the VAXA system imaging an actual vehicle, and we see that they're smuggling two people are smuggled in that vehicle. So it's a very useful tool for the customs folks. We also have computer tomography scanners at the airports that they can visualize the contents of your luggage. So like we just saw, trained canine detection teams are the gold standard for trace detection out on the field. And here we see his handler and his canine searching packages in a warehouse. And we also have ion mobility spectrometry, which some of you have experience with. Amplifying fluorescent polymers. And these are polymers that are linked they're chromophores that are linked in a molecular wire. And when they come into contact with an analyte such as TNT, the fluorescence will quench and you can see a response. But because they're chained in this molecular wire, you can have a small amount of analyte produce enough signal. So it's kind of analogous to when you have a Christmas light set and one light bulb goes out. Usually, all the light bulbs go out. So that's the same concept with the amplifying fluorescent polymers. And that's why you can get down to the part per trillion levels. Then we also have the colorimetric kits that show a distinct color change for explosives being present. So for contraband detection, we have two different strategies. We can go for trace and bulk detection. And these are considered complementary. So when we're looking for a trace sample, we're targeting, we're in a scenario where we're trying to show that this person has handled explosives or has become close in proximity to them. We're looking for microscopic amounts. So we can't really see these with the naked eye, so we need help of a microscope or these very sensitive trace detectors, which are chemical sensors. They're highly specific as compared to the bulk detectors, which are just imaging the contents of a container. And the bulk detection, we're actually looking for the large amount of material that is being obscured, whereas with the trace, we're looking for small quantities, which could either be the particles or the vapors that are being emitted from a concealed package of explosives or drugs. So bulk detectors use imaging and nuclear properties to show you where the threat could possibly be. And here in the bottom, we see a current millimeter wave image that is now being used by TSA, where the body parts are not being shown anymore due to the public outcry, but it'll highlight the area where the concealment would be. Unfortunately for the bulk detectors, they are higher equipment costs, but that is mitigated by the fact that if there was an issue happening at a port of entry, obviously shutting down that port of entry would be much more costly than investing in these technologies. With trace detection, sampling is very important, a very important aspect of trace detection. Whereas in bulk, you're seeing the whole image of the inside of a container. For trace, you have to effectively be able to remove the particles from the luggage or collect that vapor that is being emitted from the drug or explosive. So that's what I mean by it being very sample dependent. On the top trace, you actually see the detection of 2,4-DNT by ion mobility spectrometry. So combining trace and bulk detection and having all these tools in our toolkit help us find that needle in the haystack. So again, to reiterate on trace detection, we're conducting chemical analysis on very small amounts of contraband material. So here we see TNT explosive. Now, like Dr. Almero was alluding to earlier, we're looking for very small quantities. So I've made this slide so you guys can visualize what we're talking about when we use these terms such as part per million or parts per billion or a nanogram. So if you think about what a nanogram is, think about a Splenda packet, and that weighs 1 gram. So imagine we're looking at a billionth of a gram when we're doing these sorts of analyses. And parts per million, you can visualize 1 inch in a 16-mile road, or more dilute would be parts per billion, which is a second in 32 years. So for trace detectors, there are 3 different steps. And the first is collecting your sample, which, like I said, is very important for trace detection. Then separating your different components and analyzing them to produce an alarm, and gives the operator an indication that there is possibly a threat agent present. So for collection, sample acquisition, again, is very key. You have to be able to collect that sample, whether it be particles or vapors, effectively. Now, pre-concentration is also important because you might have a minute amount of vapor available in a large volume area of air. So you're not going to evacuate all of the air of a room to get that small portion of the odor. So you need to efficiently be able to pre-concentrate that or screen it down. And then once you've collected it, you have to have a method of introducing your sample into your instrument. So the next step is actually separating the different compounds that you collect. So you take a sample and you might have 500 to 300 components in there. But an efficient trace detector gives you selectivity towards that specific contraband. So you can modify instrumental parameters to preferentially produce peaks that are only for your compound that you're searching for. And a good trace detector would resolve multiple indicators of contraband. So there was a question about if you had a plasticizer and that's ubiquitous in the environment. Well, you would look for that, but then you would also have probably another detection channel where you see, let's say, a volatile component of the explosives, such as for instance, smokeless powders. You'll have nitroglycerin, which has a high vapor pressure. So you'll see that compound along with the other additives to the smokeless powder. So that's what I mean by a good trace detector gives you multiple indicators of contraband. And I'll also call this channels. And lastly, we analyze. And the important aspect of trace detection is that it's fast and simple to interpret the results. So here's the point where we actually detect the contraband. And trace detectors vary in their sensitivity, or the amount of difference you see with concentration differences in your signal, and the actual detection limits, or how low can you go? What is the smallest amount that can be detected? So we have a variety of trace samples that we can analyze with instruments. So first we have to have a source. So like we saw earlier with the dog, he had a source that contained marijuana, and that was emitting volatiles that were coming off of the packet where he had it contained. You can also have particles. So here we have some TATB particles that are imaged by SEM. And below, we actually have these COMPS bags. They're called controlled odor mimic permeation systems. And they're actually simply just a low-density polyethylene bag that contains our compound of interest, which in this case is 2,4-DNT, which is degradation product of TNT or an additive in smokeless powders. Now, from studying the weight changes over long periods of time, we can know how much mass is coming off of this bag per second. So that's why we use these COMPS bags for training aids for the canines. So when we present this to the canine, we know, okay, it's been emitting X nanograms per second, so for a given amount of time, we know how much odor is available. So it's a good way of training them and having equality in the amount of odor that they're all being trained on. And for our purposes, we actually use these COMPS devices to calibrate the PCBME IMS system. So again, to reiterate, particles are these microscopic material of contraband that get stuck to the surfaces. Now, you'll be able to see them when, for instance, a bomb maker is touching the bomb and he's not being careful about using gloves or the transfer of particles to the object, the exterior of the object. When we sample for vapors, we're looking again for these molecules that are emitted from the solid or the liquid explosive. And we have options in sampling either particles or vapors. And on the top, we see the analyst swiping a surface. And that's considered contact, because contact is being made between the swab material and the surface that is suspected of containing the contraband. Then below that, we have non-contact. And some of us have been in situations in the airport where we're placed in the people sampler, where they puff air all up and down our bodies in order to dislodge any potential particles that you may have from handling drugs during packaging or explosives. And those are directed into the analyzer to show that there's presence or not of drugs or explosives. And lastly, vapor detection is obviously done with non-contact techniques, because again, it's coming off of the actual drug or explosive. So here's a schematic of the processes that are going on in the ion mobility spectrometer. So again, key is collecting your sample. So you have to have it on some sort of medium, and you place it into the heated desorber, and all of the IMS instruments have this type of desorption unit. And this heat vaporizes your sample into gas molecules. These molecules are directed into what's called the ionization region, and they're being ionized through a series of chemical reactions. And you can even introduce a dopant gas that will selectively ionize certain compounds and prevent others from being ionized themselves. So these ions are gated into the drift region, and under a uniform electric field, they're propelled towards the detector. Now, separation occurs due to differences in your ions based on shape, size, mass, and charge. So we have this counterflow of drift gas that is coming against the ions that are traveling towards the detector. So if you can visualize it as a man in a crowd trying to go against it, he's going to have a harder time than a small child running through the crowd. He'll get to his destination faster. And that's the principle here. And we're just looking at the time of flight from the moment that the ions exit the shutter to the detector. And then based on that mobility, we can presumptively identify the compounds that we're seeking. So ion mobility spectrometry is it's used very much in the airport scenario. More than 15,000 instruments conduct over 10 million analyses per year. And much of this is due to the fact that the analysis is low cost, and the instruments are very easy to operate, which we will see soon. It's very portable. It can actually be made into handheld instruments that weigh less than 10 pounds. And this is because they undergo, the processes that undergo within the ion mobility spectrometer are atmospheric pressure chemical ionization. And that simply just means that we don't need these high vacuum systems or high purity gases. So it makes it very portable. It's very sensitive down to the picogram range. And IMS is advantageous because for explosives, we obtain very stable negative product ions, and for the drugs, we obtain favorable positive ion response towards these nitrogen-containing compounds. And as of late, we have dual mode analyzers, so we can see our compounds in positive and negative mode. So simultaneously, you can take one sample and see if it's a drug or an explosive. But with all instrumentation, you have disadvantages, of course. And one of the main ones is that most commercial IMS systems today include a radioactive source. But they're trying to move away from that now. And again, like I alluded to earlier, the detection channels that are programmed into these instruments are based only on the actual parent explosives, such as RDX and THC, not the odor signatures that the canines are alerting to. It's an efficient particle sampler, but the vapor sampling needs help because it doesn't have an efficient sample introduction and collection mechanism. And that's what PSPME was designed to do. So here we're going to see a video of the use of an Itomizer 3 instrument in a club scene.
North Wales Police are working with partner agencies to protect individuals, their families and communities from the use of illicit drugs. This evening we have deployed the GE Iron Track Itomizer to local licensed premises. The device is a desktop drug and explosives detection and identification system. It is capable of detecting traces of a set number of drugs on people or from any surface. This is part of our overall drug strategy and will assist in identifying and apprehending offenders and detect offences of possession and supply of controlled drugs. By doing this, we aim to provide a safer environment for members of the public to use licensed premises while supporting members of the licensing trade in their efforts to discourage the use of controlled drugs within their premises. The Itomizer enables an objective assessment to be made of the likelihood of an individual having had contact with controlled drugs and as a consequence removes the guesswork from the discretionary exercise of police powers. In effect, it provides an objective basis on which reasonable grounds can be established for the exercise of police powers. If you have any concerns about drugs in your community, please contact your local policing team or call Crime Stoppers on 0800 555 111. If you want free confidential help and advice about drugs, please contact the Wales Drug and Alcohol Helpline on 0800 633 5588.
So we saw that he was conducting particle sampling and he was wiping the hands of the folks at the club. But what we want to do is move towards vapor sampling, seeing the odors that are being emanated. Okay. So here's another video explaining a little bit more about the IMS systems that we're going to be using. So this is a video concerning the Itomizer.
The Itomizer works by heating the sample in the desorber to create vapors that are drawn into the detector and electrically charged by a patented ionization process. At the front of the detector, behind the desorber, is a semi-permeable membrane. Narcotics and explosives easily pass through the membrane, but inorganic materials and water vapor cannot. Once they pass through the membrane, the vapors reach the ionization chamber, where they gain or lose electrons and become positively or negatively charged. In the ionization chamber, the vapors react with dopant gases. The dopants are circulated inside the detector by the same pump that draws the sample into the detector. The dopants help to ensure that contraband substances are fully ionized and simultaneously prevent the ionization of other substances that are not targeted for detection. Once the ions are created, an electric field is used to propel them from the ion trap at the front of the detector to the collector electrode at the other end. The current generated by the ions creates peaks that are displayed as a plasmagram. By measuring the time of flight of the ions, substances may be identified. This process allows detection of targeted contraband substances with high sensitivity and selectivity.
So the first instrument that we'll be using is the Itomizer 3E, and this one conducts both positive and negative detection, so we can simultaneously see drugs and explosives. The analysis is done in as little as 8 seconds, and we have the option of doing wipe sampling, as you see below, or vacuum sampling. But with the vacuum sampling, there's no pre-concentration. So you're just trying to suck air and hopefully dislodge particles and trap them on that swab material, and then you introduce it into the desorber. And generally, these instruments are very easy to use. The next one is the handheld IMS system from Morpho Detection. It's called the Mobile Trace, and it weighs only 9.4 pounds. It collects both it detects both particles and vapors, but you'll see that with particles, you have the nozzle of the desorber that you would have to remove for detection of vapors. But again, there's no pre-concentration like PSPME would provide with this instrument. Again, this is also simultaneous dual mode detection, so we can see our volatile chemical signatures both in the positive and negative mode, which is advantageous. And again, the analysis is done in as little as 8 seconds. So differential mobility spectrometry is the next technique that we'll be using. And in traditional IMS, the mobility is considered constant for a certain electric field. But once you increase that electric field beyond a certain point, then the mobility of that ion depends more on the strength of the electric field. So the ions, you have to find a way to introduce your sample. They're ionized, just as in IMS. But there is no shutter on the DMS systems. So it's advantageous in that you have a 100% duty cycle, so you're not pulsing your ions into the detector. You have 2 plates, and an RF voltage is applied to one of them. And that RF is perpendicular to the actual gas flow. So the ions are going to want to go to either the top electrode or the bottom electrode. But if they go up to the top electrode or the bottom electrode, they'll get neutralized. So in order to steer the ions through the 2 parallel plates to the detector, you need to introduce a compensation voltage. So during a scan, you have many compensation voltages that it's modified. So you have a full scan of positive and negative compensation voltages, and as it hits the detector, you'll see this compensation voltage DMS spectrum here. You'll see the different species being separated. So separation here is, as opposed to IMS, is based on the changes in mobility in response to these applied fields. So what Thermo Scientific did was they married gas chromatography, which is a technique used to separate a large number of compounds, with the DMS side of it by micro DMX, which is by Cyanex. So the advantages are that with the DMS, you get simultaneous positive and negative mode detection, but at the same time, you're adding a fast pre-separation. So the total analysis time is 16 seconds. And this goes back to the whole idea of resolving multiple threats to give you more of an idea of what's contained in the sample. So you'll have multiple peaks, and you can actually identify them based on your DMS output. And currently, these instruments are deployed at over 170 airports around the world. Okay. So now these volatile chemical signatures that the dogs are honing in on, how did we determine that these are the compounds that are being emitted? Well, the first step is to conduct headspace analysis. So we take a small amount of drug or explosive, and we sample the air that is above it. So then we'll introduce that sample into the instrument, such as a GCDMS, and we'll obtain identification of these compounds. We can also present the suspected compounds to the dogs that are already trained on drugs. So if we have a suspected odor signature for a certain drug, we can obtain the dog that is trained on that drug and see if we present that odor signature if they alert to it. And these are the type of studies that have been done at FIU, at Dr. Furton's group and Dr. Amral's group. So volatile chemical signatures, again, are coming off of the drugs and explosives. And for instance, as Dr. Amral said earlier, methylbenzoate, a degradation product of cocaine, has been proven to be detected by the dogs. For marijuana, we have limonene, alpha-pinene, and beta-pinene that have been shown by headspace analysis to be coming off of the marijuana. Also for RDX, we have the option of sampling cyclohexanone, and that has a high vapor pressure compared to RDX. So for the smokeless powders, we have the volatiles 2,4-DMT, DPA, and EC that can be targeted. So again, the commercial instruments are not configured to detect these compounds. So we want to take advantage of this knowledge that we have now about which are the compounds that are being detected or that are coming off of the drugs in order to use what we currently have available for detection. So in order to configure the instruments to detect these compounds, we have to make some changes. So the ability of us to see these peaks, these instruments for these specific compounds, depends on the different operating conditions. So we can change the dopants to selectively ionize that compound. We can change the drift tube temperature to prevent the compound from breaking down as it travels through the drift tube. We can change the polarity, if a certain compound might be seen in the positive mode but not the negative mode. We can also change that drift flow that impedes movement through the drift tube or increase the sample flow. So you have to find a balance with all of these operating conditions in order to be able to detect a large suite of these volatile chemical signatures. Now, what really enabled this work was the development of what is shown here, which is the first generation SPME IMS interface. So I don't know if many of you are familiar with solid phase microextraction, but Dr. Amaral will talk a little bit more about that coming up. And it's a pre-concentration technique. So we were able to sample the drugs and explosives, collect them on this fiber, and introduce them into the IMS, and see how we can modify the conditions in order to be able to detect these compounds. So in conclusion, bulk and trace detection are complementary, and they're both very important in our toolkit for detecting drugs and explosives. Trace detection involves particle and vapor sampling, and the detection of vapors that are coming off of the parent drugs and explosives may require changes in instruments that are currently manufactured in their operating conditions. Vapor detection using commercial trace detectors can be improved with pre-concentration, and they currently do not have any pre-concentration technique. And that's what we aim to show you here at this workshop, the power of the p-SPME when it's interfaced to ion mobility spectrometry. And here's some scientific references if you want to go back and refer to some of the work. Do you have any questions?
So the Aegis uses a nickel-63 for ionization? Yeah, so it's not a equivalent discharge. It's radioactive, the nickel-63. And the with the GC front end, sometimes there are problems with contaminating it or introducing too much compound and saturating it, and then you sometimes have to either clean it or replace it. Are there protocols to minimize that from happening that are included with the?
Well, generally, you want to swipe a sample, and sometimes you do get a large hit. But the instrument itself has a clean cycle mechanism that puffs air through and actually solvent through to clear out that contamination if it's too much. Okay, thank you.